balance between forward and reverse reactions.
And changes in experimental condition can disturb and shift the position of the equilibrium so that more or less of the products is formed.
And the controllable variables that affect the chemical equilibrium are concentration, pressure, volume, and temperature.
And today, we're going to examine how each of these variables can affect a reacting system at equilibrium.
There is a general rule that helps us predict the direction in which an equilibrium reaction will move.
If there is a change in concentration, pressure, volume, and temperature,
The rule, known as Le Chatelier's principle, named after the French chemist Henri Le Chatelier, states that
if an external stress is applied to a system at equilibrium, the system adjusts in a way that the stress is partially offset as it tries to re-establish equilibrium.
the word stress means a change in concentration, pressure, volume, and temperature that removes a system from the equilibrium state.
And we are going to utilize Le Chatelier's principle to assess the effects of these changes. Let's proceed to the changes in concentrations. So let's use this representation as our example. Your R stands for your reactant and the P stands for your product. So as you can see, the reactant is at equilibrium with your product. If we're going to increase the concentration of our product, according to Le Chatelier's principle, the shift in equilibrium would be from right to left, since we need to offset this stress, which is the increase of concentration. On the other hand, if we are going to decrease the concentration of our product, according also to the principle, the shift in equilibrium would then be from left to right, since we need to offset the stress, which is the decrease in concentration. And that also would apply if we're going to increase and decrease our reactant.
We are now done discussing the changes in concentration, and now we are going to move on to the changes in pressure and volume. Concentrations of gases are greatly affected by changes in pressure, and ordinarily not the concentrations of reacting species in condensed phases, because liquids and solids are incompressible. Since we are tackling the changes in pressure and volume, let us recall the ideal gas law, which has the equation PV is equal to nRT, and this law suggests that pressure is inversely proportional to volume and directly proportional to the number of moles. And this law is very significant for our topic. Suppose we have this equation at equilibrium, considering these two are gases, and here we have 1 mole for our reactant and 2 moles for our product. According to the principle, if we increase the pressure for our gases, the shift will favor the side of the equation which has the lesser moles. So this shift will be from right to left. On the other hand, if we decrease the pressure of these gases, that will be a different case, because the shift will favor now the side of the equation which has now the greater number of moles. So the shift will be from left to right. There are some cases in which there is no change in the number of moles of gases. For example, in this equation, we have A plus B is equilibrium to C plus D, considering these are gases. And as you can see, the number of moles of the product is equal to the number of moles of the reactant, so a change in pressure has no effect in the equilibrium. As I said a while ago, ideal gas law has a relation with this. So you might be encountering some problems stating not a change in pressure but a change in volume. Just remember, an increase in pressure is a decrease in volume, and a decrease in pressure is an increase in volume.
For the last factor affecting the chemical equilibrium, let's have the changes in temperature. A change in concentration, pressure, or volume may alter the equilibrium position, but only a change in temperature can alter the value of the equilibrium constant. Upon the application of heat in the system, This is now an endothermic reaction. An increase in temperature favors an endothermic reaction. According to the principle, the shift would be from left to right. This is a forward reaction. On the other hand, for the exothermic reaction, wherein there is a release of heat, the shift would be from right to left because a decrease in temperature favors an exothermic reaction. Consequently, the equilibrium constant increases when the system is heated and decreases when the system is cooled.
So today, you've just learned the factors that may affect equilibrium position.
We have considered 4 ways to affect a reacting system at equilibrium.
And it is very important to remember that only a change in temperature can alter the value of the equilibrium constant. So that sums it up, and
Thank you for watching!